Hello and welcome back to the video series of finite element analysis. I am Bhavik Soneji, and today we are going to see a numerical on the dynamic problem. So let's get started. So in the previous video we have seen the consistent and lump mass matrix, and we have seen the vibration problem of rod and beam. So in today's video let's understand how to solve the numerical which is based on the vibration of a rod. So first of all, uh, let's understand the problem statement. Here, find the natural frequencies and the eigenvalues for the step bar problem. The material properties are given. So as we know the material properties, the rho is given, density of the material, and the elasticity of material is given, which is 8500 kg per meter cube, and the modulus of elasticity is given 30 into 10 raised to 10 Newton per meter square. So these two values we know. Now we want to find the eigenvalues and the frequency. What is the natural frequency of this system? So let's get started. How to get the solution? So we can get the solution by the governing equation we have. Stiffness matrix minus omega square mass matrix into displacement is equal to 0. Here the free vibrations we have considered the free vibration. So this is inspired from the equation A minus eigen B into U equal to 0. So from this equation we can solve our problem. So now first we need to find the natural frequency. That means we need to find the omega here, and the eigenvalue same, lambda and omega. So these two things we need to find: omega value, radian per second, and eigenvalue. So that is our purpose. Now how we can solve this problem? So here you can see there are two elements, element number 1. So we start from the element number 1 first. So in the element number 1, the stiffness matrix would be A1 E1 divided by L1 into 1 minus 1 minus 1 1. So this derivation we have already done in the previous videos, so we are directly taking the values. So here the element number 1 is for node number 1 and node number 2. So there are total 3 nodes: node 1, 2 and 3. So element number 1 is in between node number 1 and node number 2. So we can write 1 2 1 2. So now if we are putting the values, we have area is equal to 1 meter square, modulus of elasticity 30 into 10 raised to 10 divided by L is 10 meter. So 10. So if we evaluate this 10 got cancelled, so we have 3 into 10 raised to 10, 1 minus 1 minus 1 1. So same thing we have to do for the element number 2. So for element number 2, we have K2 stiffness matrix A2 E2 divided by L2, and this element number 2 is in between node number 2 and node number 3. So here in this stiffness matrix it would be 2 3 2 3. Same 1 minus 1 minus 1 1. Putting all this value, uh, area is 0.5, E is 30 10 is to 10, length is 5 meter. So if we calculate this, we get 3 into 10 is to 10, 1 minus 1 minus 1 1. This is for node 2 3 2 3. Now we have obtained first the stiffness matrix for elements. Same way we have to find the mass matrix for the element number 1 and element number 2. So for the first step we will find the matrix for element number 1, M1 is equal to rho A L by 6 2112. So this derivation also we have derived in the earlier video, so you can check it out. Directly we are taking the value for the mass matrix. So if we put all the values, we get the value 85 into 10 raised to 3 divided by 6 2112. Now this is element number 1, so 1212. Same for element number 2. So mass matrix for element number 2, M2 is rho AL divided by 6 2112. So putting all the values for element number 2, we have 8500.55 divided by 6 2112. So if we calculate this thing, we will get 85 into 10 is to 3 divided by 24 2112. So now we need to find the, this is the elemental stiffness matrix. So now we need to find the global stiffness matrix. So first we will find the global mass matrix. So global mass matrix, we have to include first element and second element together. So it will become capital M is equal to 3 cross 3 matrix. So first, second, third node, first, second, third node. So element number 1 is in between first and second. So here the values are 1 2 1 2. So value we have to take from here, and same for from the second mass matrix. So let's consider the common factor first. Here 85 into 10 raised to 3 divided by 24. So if we need 24 here, we need to multiply it. We need to multiply and divide by 4. So here I am multiplying it by 4. So, and in the base and in the matrix I am multiplying. So it will become 8 4 4 8. So now we can take the 85 into 10 is to 3 divided by 24 common. Now we can directly add. For 1 1 it is 8. For 1 2 it is 4. 1 3 it is 0. Same for 1 2 it is 4. 2 2 we have to add this thing, 8 plus 2, that is 10. 1 3 it is 1. Here again 0, and last two digits are 1 and 2. So now I have combined the global matrix into one matrix and obtain the global mass matrix. So in the same way we have to obtain the global stiffness matrix. So global stiffness matrix capital K, which would be 3 into 10 raised to 10 would be the common value. So 3 into 10 raised to 10. And the matrix is 3 by 3 matrix. So 1, 2, 3, 1, 2, 3. So we need to merge these two matrix which is having the same value 1 minus 1 minus 1 1. Here also for element number 2 it is 1 minus 1 minus 1 1. So combining this matrix we will get 1 minus 1 0 minus 1 2 minus 1 0 minus 1 1. So now I have prepared the global stiffness mass matrix and global mass matrix. So we can combine these two values and putting it in the free vibration equation. So if we put all these value in the free vibration equation, we will get 3 into 10 raised to 10 global stiffness matrix 1 minus 1 0 minus 1 2 minus 1 0 minus 1 1 minus omega square into 85 into 10 raised to 3 divided by 24 mass matrix, global mass matrix 8 4 0 4 10 1 0 1 2 into, with the whole bracket we need to close the bracket, into we have uh, displacement vector u1 u2 and u3 is equal to 0. So now we have put the values of global stiffness mass matrix, global mass matrix, and displacement u1 u2 u3. So u1 would be here, u2 here, and u3 here. So what we can do now, uh, we can divide whole equation by 3 into 10 raised to 10. So we have divided by same value. So here 1, 1 minus 1 0, minus 1 2, minus 1 0, minus 1 1. This whole value, if we divide by 10 cross 3 cross 10 into 10 is to 10, we will get 1.181 into 10 raised to minus 7. 1.181 into 10 raised to minus 7. This matrix will remain same: 8 4 0 4 10 1 0 1 2 into the displacement vector u1 u2 u3 is equal to 0. So now this equation is similar to the eigenvalue equation, this equation. So we can compare this equation with the what we have derived. So here the eigenvalue we can take. If we take this as my eigenvalue, so taking lambda eigenvalue is equal to 1.181 into 10 raised to minus 7 omega square. So we have a equation like this: 1 minus 1 0, minus 1 2, minus 1 0, minus 1 1, minus, instead of this whole value we have taken lambda, that is my eigen. So eigen into the mass matrix, we have 8 4 0 4 10 7 0 1 2 whole into the u1 u2 u3 equal to 0. Now in this value we need to apply the boundary condition. So applying all the boundary condition, we know that u1 equal to 0. So as you can see in this figure, this is my fixed end. So at the node number 1, the deflection will be 0 always. So I am putting this boundary condition in my this equation. So first let us multiply this eigenvalue in this value. So we have matrix which is 1 minus 8 lambda, first with first, second with second, minus 1 minus 4 lambda, this is my second, third 0 into 0, that would be 0, second column second row second element with second column, minus 1 into lambda minus 4 lambda, 2 minus 10 lambda, minus 1 minus lambda, 0 minus 1 minus lambda, and 1 minus 2 lambda into u1 u2 u3 is equal to 0. Now applying this boundary condition for u1 the row containing and the column containing value will be 0. So this matrix will be converted into, so I am crossing this first row and first column. So we have now 2 gem 2 matrix, which can be written as 2 minus 10 lambda minus 1 minus lambda minus 1 minus lambda 1 minus 2 lambda into, here the u1 will get cancelled, so u2 and u3 vector is equal to 0. So converting this value into the equation, so cross multiplication we need to do. So we will get the equation this into this. So 2 minus 10 lambda into 1 minus 2 lambda minus minus 1 minus lambda minus 1 minus lambda equal to 0. So if we calculate this equation, we have an equation like this: 2 minus 4 lambda minus 10 lambda plus 20 lambda square minus 1 plus 2 lambda plus lambda square is equal to 0. So if we calculate this value, we will get 20 lambda square minus 14 lambda plus 2 minus 1 minus 2 lambda square is equal to 0. So this equation will be 20 minus 1 lambda square, 19 lambda square minus 16 lambda minus 1 is equal to 0. So if we solve this equation, we have a method called x is equal to minus b plus or minus b square minus 4ac divided by 2a. So if we apply this rule, we will have the different values of eigen called lambda 1, which is positive value 0.0679, and lambda 2 second positive value would be 0.7742. We will get other values also, but those will be the negative values, so we need to consider the positive values only. So by solving this equation, we will get the values of, so if we solve the values of this equation, we will get the values of eigen 1 and eigen 2 in this way. So now up to first step we have done. Now we need to find the natural frequency value. So we have taken lambda is equal to 1.181 into 10 is to minus 7 omega square. So we will put these two values into omega. So first for lambda 1, 1.181 10 is to minus 7 omega 1 square, and second value we have lambda 2, 1.181 10 is to minus 7 omega 2 square. So taking the value, putting the value here, omega 1 square we have 0.0575 10 is to 7. So omega 1 we will get 57.5 10 is to 4, and omega 2 we have 0.6555 10 is to minus 7. So omega 2 would be 2560. The unit of the frequency is radian per second. So we have get the natural frequencies of our system, which is omega 1 and omega 2. So these are my natural frequencies. So in this way, we can solve any kind of problem. Hope you find it useful, and thank you.